Today, we're looking at VSEPR. We did a brief PowerPoint on VSEPR and talking about limitations of Lewis structures and moving to how we work out A's, X's, and E's. This is a sheet I want you to use. And what's going to happen is we are going to make some Lewis structures and you'll be able to fill them in here. And then this will be the structural diagram. And so in some cases it's largely done, and in other cases you're going to have to add in the information as we go. So here this will be a Lewis structure, and this will end up being a structural diagram. So that's kind of what this mumbo jumbo is about. I'm going to use a PowerPoint because it's sort of easier for me to show. And also I'm going to do it sort of section by section. So I'm going to do the 1, 2, 3 in this video. I'll also have another video where I show you the Lewis structures, and we'll do some stick and styrofoam ball molecules or molecular kit molecules. And then we'll just keep going back and forth as we go through the 4, 5, and 6 electron pairs. So this is where you're going to be starting with the PowerPoint right there. So your mission is to do a Lewis structure. From the Lewis structure, you're going to find the central atom. You're going to look at the number of atoms bonded to it. That's going to be your X value. And then you're going to look at number of lone pairs left from the central atom, which will typically be 0, 1, 2, or 3. Once you have the A's, X's, and E's, you're going to look it up on a chart, and that's going to tell you the corresponding shape. So I don't expect you to fully get it from watching these PowerPoints. This is our introduction. We're laying the groundwork. And then as we do more and more examples, it will become straightforward. So if I look at HCl, and I'm doing a Lewis structure, so there we have our H and our Cl. We know H is satisfied by the 2 electrons, and the Cl needs to have 8. But this is a case where, let's call Cl our central atom. Well, there's only one atom bonded to it. It doesn't even matter about the lone pairs, so we don't even bother writing that down. So AX is linear. Anytime we have just 2 atoms together, it's linear. And so this is what's called a space-filled molecule or representation. But typically for a structural diagram, I would go H, and then I put a line representing the bond, and then I put in Cl, and I'm done. That's a big C, little l. Hopefully that makes sense. Well, let's try 2 electron pairs and see what we get. And maybe I should try a better color here. Let's see if we give me a choice on colors. Come on. Looks like I'm stuck with red here. Okay, so if I do BCl2, it turns out to be a violator. And apologies, the red is what's coming through here. Beryllium is satisfied with 2 bonds or 4 electrons around it. Now, in this case, the chlorine is, you have a chlorine on either side, and we have to get it up to 8. And now we want to show you why it's AX2. So the A, in this case, is the beryllium. We have 1 central atom. The X refers to chlorine, and we have 2 chlorine, so it's AX2, and there are no lone pairs left on beryllium. So it is linear, and that's one weird way of, I just lost my Lewis structure. So if I'm drawing it out, being linear, it means straight line, chlorines on opposite sides. I can't put a chlorine up here or make it 90 degrees. VSEPR says these things want to get as far away from each other, and this way the pairs of electrons involved in bonding are 180 degrees apart. So here's 3 electron pairs, and we have BF3. This is another violator. So we have B. Oh, it might be letting me change color. Let me change color. Can't stand that. Okay. So let's see, yellow. So here's our B. And boron is happy with 3 bonds or 6 electrons around it. So it goes B, F, and F, and F, And then we put our dots around. We say, wasn't that fun? Those are supposed to be dots, not squashed insects. Okay, so now we have octets around the 3 fluorines. We have 3 bonds around the boron. It says it's trigonal planar. That means it can be a very flat structure. Anytime you see planar, it means flat. It'll sit flat on a table. And that means we want our angles. Yeah, that was terrible. Ignore that. Let me use my, well, we'll black it out in a second here. Okay, come on, just about there. So, we're going to have 120 degrees between each of these. Let's see if it'll give me a black here. Can we get a black? Excellent, we can have a blackout. See, now you'll never know that was there. Totally gone. Beautiful. So this is 120 degrees between each of the angles. That's how we're going to get those pairs of electrons as far apart from each other as possible. Now let's see if we got another one here to deal with. So that's the Lewis structure. And notice they use Cl instead of F when I hijack that. And this is trying to show this trigonal planar structure. And let's see, we have one last example with 3 electron pairs. And this is going to be AX2E. Now sulfur dioxide, let's see if it gives me a Lewis structure. Pretty blurry one, so let's try, see if I'm still in yellow mode. Let's backtrack. Okay, let's try yellow. That seemed to show up. Come on, there he is. Okay, so when I look at SO2, it's what's called a resonance structure. You shouldn't know about it at this point. That's something that comes up later. And what it means is we get a double bond on one side and a single bond on the other. And we go boom, boom, boom. And those are supposed to be electron dots. So there's 8 around that oxygen. It already has 4 there. So we put 2 above it, 2 below it. And the sulfur only has 6, so we put a lone pair right here. So when we look at this, we say, okay, here's the sulfur, that's our A. 2 atoms bonded to it, so that's our O2. 1 lone pair left on it, so it's AX2E. Now, you're going to say, does this double bond matter? And it doesn't. Notice all this is saying is atoms bonded directly to it. Doesn't matter if it's a double or single bond. So A, X2, lone pair is our E, and it has a bent shape. Instead of being linear, it is going to be bent. Let's see if we have a bent one coming in there. This is trying to represent the lone pair there. And so if I was drawing it out, I would go like this. I would go S, and I'd go, there's my double bond. That's supposed to be a double bond. Boom, and boom. And that's another oxygen. And what we're trying to show, it definitely is not a straight line. I like using the word bent. Sometimes you'll see angular. Bent is a 4-letter word, so it's much better to use. So that wraps up going from 1 to 3 electron pairs. Next video will be about, next video will show you these structures. And then after that, the next video will be on 4 electron pairs.